Okay. Uh, Welcome to the 8th TA session. Um, in this course, Principles of Signals and Systems, uh, offered by Professor Aditya Jagannatham from IIT Kanpur through NPTEL. My name is Yashvanth. I'm presently a PhD student at the Department of EC in IISc Bangalore. I work with Professor Chandramurthy, and my research interests lie in signal processing and wireless comm systems. And I currently focus on intelligent reflecting surfaces for 5G and beyond wireless comm. Okay, so the topics for this week were broadly on solving varieties of problems related to Fourier series and transforms. So, in general, problems on Fourier analysis. Um, and in continuation of that, today's session, we will solve quite a number of problems in Fourier transforms. I think the last class we had dealt a lot in Fourier series, and we had seen how easily you can solve very difficult problems just by using the properties of Fourier series and etc. So today we will focus on Fourier transforms completely. We will again see how well we can use properties of Fourier transforms to simplify the solution to any even a very difficult problem. Okay, so part one, as usual, summary, but this summary is going to be quite short again because mostly session in this week. So it's a very short summary. We'll soon get into the tutorials part. Okay, so recall that Fourier transform is defined for continuous time aperiodic signal, and the definition of Fourier transform goes as follows. You have the notion of what is called the frequency. So this omega is what is called the angular frequency. So x of omega is defined as integral minus infinity to plus infinity x of t e power minus j omega t dt. Okay, or equivalently, if you just want to write in the linear frequency domain, it's x of f equals minus integral minus infinity to plus infinity x of t e power minus j 2 pi f t dt. So the only difference is that if you look at these two relations, you put omega equal to 2 pi f, you get the relation in the other representation. Okay, so essentially Fourier transform allows you to represent a time domain signal in the frequency domain. Okay, so if you have a x of t, you come to this integral operation. That is the value of the signal on the frequency omega, or at frequency f, x of f will represent what is the component, what is the signal energy, sorry, the amplitude of the signal on the frequency f. That's basically the physical understanding of a Fourier transform. Similarly, one can define inverse Fourier transform, that is given x of omega. How will you recover back your time domain signal x of t? That is given, that is called if you have x of omega in hand, then the x of t is defined given by 1 by 2 pi integral minus infinity to plus infinity x of omega e power j omega t d omega. Or if we have x of f with us, then x of t equal to minus infinity to plus infinity x of f e power j 2 pi f t df. Okay, so this is the way you take the inverse Fourier transform, and this is a table which basically tells the properties of Fourier transform, which is taken from chapter number 4 of the reference Oppenheim Signals and Systems. I am not going to go over this table because last class we went through this table one by one, but I have inserted this table here because in today's problems we will come back and refer this table for properties of Fourier transform whenever we need. Okay, fine. This is a main summary, actual summary for this week. So what I'm going to do is I'm going to quickly recollect some standard Fourier pairs, Fourier transform pairs that were discussed in class or solved in class. So if x of t equal to signal number 1, x of t equal to e power minus a mod of t for a greater than 0. That is the time domain signal. Well, if you plot the time domain signal x of t as a function of t, okay, this is not x of t, this is just t, then essentially you can show that the signal axis either negative t or positive t, okay, in exponential manner. That is a plot for x of t. Now if you compute the Fourier transform of this signal, you can show that x of omega is given as 2a by a square plus omega square, and that also has a decay form because this is a decreasing function in omega. X of omega, when you plot as a function of omega, this also decreases. This is This is basically the Fourier series transform of x of t equal to e power minus a mod t. Similarly, if you have x of t is equal to cos omega naught t, your Fourier transform is given by pi times delta of omega minus omega naught plus pi times delta of omega plus omega naught. That is, you will have an impulse function at minus omega naught and plus omega naught. You will have the means, what does it mean? Namely that this signal says that it has only two frequency components, one is at minus omega naught and plus omega naught. That is not surprising because x of t is cos omega naught t, which means it is a basically has the frequency is omega naught. Therefore, you should have a non-zero value only at omega naught or plus minus omega naught, because cos of minus omega naught is also the same as cos of plus omega naught t. Okay, so only at minus omega naught and plus omega naught you should have some non-zero value, and that's what this equation also says. The third function is called x of t equal to signum function, that is sine of t or signum of t. It takes the value 1 and it takes the value minus 1 for 1 for positive time axis and minus 1 for negative time axis. Then basically if you work out the Fourier transform of this signal, you can show that x of omega equal to 2 by j omega. That is, it is a hyperbola. Okay, this is 1 by x form, right? Y is equal to 1 by x. So if you plot with respect to x, it is just like this. That's what is this x of omega. And finally, you have x of t equal to u of t. U of t is a unit step function. That is, for negative t axis, you have 0, and positive t axis, you have plus 1. Okay, this is called a unit step function. And if you compute the Fourier transform of a unit step function, that comes out to be x of omega equal to pi times delta of omega plus 1 by j omega. Okay, fine. So this is basically the short, very quick summary of this week's lecture. Are there any questions? Okay, are there any questions?
No, sir.
Okay, great. So now we will start with our problem solving session. So what I have decided for this week is to solve in real time, because I felt that there are many have to be explained. So I thought I will solve in real time. Okay. So the first question is, let x of t, 1 minute, let x of t have Fourier transform capital X of omega. The question is, then what is the inverse Fourier transform of, sorry, f should be capital, Fourier transform of small x of omega? Did you understand? What it says is, the question is this, very simple. If small x of t is a time domain signal that has a function x, capital X as a Fourier transform, if I consider the small x function as the Fourier frequency domain function, then what is the corresponding time domain signal, inverse Fourier transform, for which small x of omega is a Fourier transform? That is what is this question asking. Any leads? How will I solve? You want to try out, like what will be the first step in this, or any ideas? What does something strike to you? How to proceed? Which property of Fourier transform can I use here? Yes. Okay, I will tell you. We will use a duality property of Fourier transform. Okay, what it says, duality property, if small x of t has the Fourier transform capital X of omega, then capital X of t has a Fourier transform. Yes, can anyone complete? What is the Fourier transform of capital X of t? Yes. 2 pi into small x of minus omega. Is this correct? This is a property of duality property of Fourier transform. You see, this is what we discussed in this table also. You see, if x of t, small x of t has a Fourier transform capital X of omega, then this capital X function, when it is a time domain function, its corresponding Fourier transform will be 2 pi times small x of minus omega. This is called the duality property. That's what is I'm writing down that only. Let's now, if that is the case, what is it? If that is the case, then by what I will do is I'll bring this 2 pi to RHS. So that means 2 pi 1 by 2 pi into capital X of t has the Fourier transform small x of minus omega. And therefore, what I will do is that okay, another thing. Okay, fine. That means what does this mean? This means that um, x of minus omega, it can be given by 1 by 2 pi integral. Okay, maybe wait. So okay, now I'll ask you the question. If I just make this x of omega, now what should be left hand side? 1 by 2 pi x of t has a Fourier transform x of minus omega. Now, if I make minus omega plus omega, then how should that what is the corresponding time domain signal? Yes, can anyone tell me?
X of minus t.
Exactly. Is it just that? It is 1 by 2 pi into capital X of minus t. Because it's 1 by 2 pi carries over. Okay. Therefore, inverse Fourier transform of small x of omega equal to 1 by 2 pi capital X of minus t. Okay, that's a asked question. Is it clear? Okay, let's continue the second question. So what I'm going to consider is consider the following time domain signal. So basically what it says is the time domain signal is as follows. This is a function of t and this is x of t. It takes a value 1 for negative t-axis. It takes a value minus 1 for positive t-axis. And it takes a value 0 at 0. At t equal to 0, it takes a value 0. I will wait. Oops. Okay. It takes a value 1 when t is less than 0. It takes a value 0 at t equal to 0. It takes a value minus 1 when t is greater than 0. Okay. Now question is again simple. Find the Fourier transform. Okay. Any leads? Any idea how do I solve this? Without just by using properties of Fourier transform. Of course, you can use the definition integration x of t per minus j omega t dt and then apply this, use the definition of the integrated and then solve. That's one way.
It's signum function.
Is it signum function? See the signum function takes a value 1 for positive t-axis and minus 1 for negative t-axis. But here I have positive it takes a value 1 for negative t-axis and minus 1 for positive t-axis. So it's not signum function, but you're right in one sense. It's some function of signum function. So what is that? Okay, I will write it down. You see whether it's correct. X of t equal to minus signum function of t. Is it correct?
Yes, sir.
Because signum, excuse me, signum function will take the value 1 if t is positive, but this minus will make -1. Then that is why t is positive means -1. Similarly, signum of t takes a negative value when t is less than 0, but there's a minus outside, so minus of -1 will become +1, and that is basically this one. So this x of t is basically negative of signum function. That's all. That means what? By linearity of Fourier transforms, what we know is that x of omega equal to minus Fourier transform of signum of t. Now, what is Fourier transform of signum of t? It was solved in class. 2 by j omega. Therefore, it is just minus 2 by j omega. That's all. Simple. Okay. Let's do the next question. Okay. So I know that the frequency response, given the frequency response, okay, the frequency response means basically the Fourier transform of the system, the impulse response. The Fourier transform of the impulse response of a system is called frequency response. Let's say the frequency response of a system is given as follows: h of omega equal to 100 plus j omega the whole square by 1 plus j omega into 10 plus j omega into 1000 plus j omega. Now the question is, what is the slope of the magnitude, okay, mod of h of omega as versus omega when omega lies between omega is a number which is much greater than 100 but much smaller than 1000. Okay, so what essentially I'm saying is, let this some h of omega. This is a complex number. See, it's a because j is coming, so it is a complex number. Okay, therefore this h of omega is a complex number for different omega. So you can find the magnitude of h of omega. Let's say the magnitude of h of omega comes out to be some graph, no problem. You take omega, which is much greater than 100 but much smaller than 1000. Now you have the curve in this region. I'm asking, what is the slope of this modulus magnitude of h of omega when omega is between somewhere which is much larger than 100 but much smaller than 1000? That's the question. For your information, just a side information, this this curve which plots the magnitude of the Fourier frequency response of a system as a function of frequency is also called Bode magnitude plot or simply Bode plot. Okay. So there is a course called Control Systems, which some of you may be taking or would have taken already. So in that course, they deal with these kind of metrics. What is a Bode plot of a system, and understand the phase response, magnitude response, and all these things. But maybe that's not very important to this question, but just side information. The question just says that h of omega is like this. You plot the magnitude spectrum of this h of omega and tell me what is the slope of this magnitude spectrum when omega is between omega is a number which is much higher, larger than 100 but much smaller than 1000. That is a question. Okay, let's do it. Solution. So simple again, it's basically based on approximation. See, one thing we need to understand, it's an engineering course. See, engineering is about trying to model things or trying to understand things which are of more practical significance. Okay, so you can do approximations in engineering as long as it captures the correct, the correct correct characteristics of the process. Okay, so you can do approximation, and we will see that this approximation is what is going to help us solve this problem. Okay, so you see what are there in this terms? It has 100 plus j omega, 1 plus j omega, 10 plus j omega, 1000 plus j omega. Okay, what I'm saying is omega is much smaller than 100, much smaller, much greater than 100, and much smaller than 1000. I'm going to crucially use this fact. If omega is a number which is much smaller than 1000, then, sorry, much greater than 100, not 1000, much greater than 100, then 1 plus j omega is approximately equal to j omega. Do you agree? Because it's like, let's say 1 plus 500j. Right. So if you look at this, if you look at the wherever, so it's 1 comma 500, right? So 1 is here and 500, let's say, is here. It's approximately here. So it's almost, this one distance is not that significant. For example, if you take mod of 1 plus 500j, it's approximately equal to 500, maybe 500 point x, doesn't matter. But it's very important to know that this one is something very small compared to 500j. So is it okay to say that 1 plus j omega is approximately equal to j omega when omega is much larger than 100? Is it okay? Yes, can anyone confirm?
Yes, sir.
Okay, yeah, great. On the same token, if you are okay with this, then the solution is very easy. So 1 plus j omega is approximately j omega. Similarly, 100 plus j omega is also approximately equal to j omega, because anyways omega is a much larger number than 100, so 100 will be negligible compared to omega number. So 100 plus j omega is also equal to j omega. 10 plus j omega is also equal to j omega. Because if omega is much larger than 100, obviously it should be much larger than 10 and 1. Okay, that is number one. Now, number two, if omega is much smaller than 1000, then tell me what is 1000 plus j omega approximately?
1000.
Sorry, can you repeat?
1000.
Correct, 1000. That's all. See, now what you do? 1 plus j omega replaced by j omega. 10 plus j omega replaced by j omega. 1000 plus j omega replaced by j omega. Now 100 plus, sorry, 1000 plus j omega replaced by
1000.
1000. And 100 plus j omega square replaced by j omega square. That's all we're going to do. Simple. Okay. Therefore, all approximation only, h of omega is approximately equal to
1
100
by
plus j
1000.
omega. Yeah, let's solve it. So it is 100 plus j omega square. 1 plus j omega is approximately j omega into j omega into 1000. Okay, which is nothing but 1 by 1000. You are right. Now tell me what is the answer. You got h of omega. For when this is correct, when omega is a much greater than 100 and much smaller than 1000, h of omega is approximately 1 by 1000. Now, what is the question? The question is asking slope of this curve. Mod of h of omega. Mod of h of omega is mod of 1 by 1000, which is 1 by 1000. So what is the slope of this curve? Tell me. So basically, it's a constant, right? Slope means you need to differentiate, right? What is the differentiate with respect to omega? Now, what is the differentiation of this with respect to omega? 1 by 1000 is a constant, right? So differentiation is
0.
0. Therefore, slope is 0. That's all. That's the answer. This question tells how you can do approximations, but still they are going to be very useful in engineering. That's the main aim of this question. Okay. Next is a little interesting question, but you need to very carefully uh, listen to this question. This is question number 4. Okay. Let x of t and y of t be two signals with Fourier transforms x of omega and y of omega. Then the question is evaluate integral minus infinity to plus infinity x of minus omega into y conjugate of omega d omega in terms of x of t and y of t. I'm asking that what this integral, right? What is the value of the integral in terms of x of t and y of t? That is a question. Okay, so this question will purely, help us to understand how can we use the properties of Fourier transform nicely. Okay, that's basically, in fact, I think this question is very also has been asked in previous assignments, I guess, in the same course. So previous assignment question, I think. Okay, so we'll solve this. It will tell very nicely how you can use the Fourier transform properties. For this, first what I will do is I will define. Okay, I will define. Okay, I'm going to first consider the convolution of the signal x of minus omega and y conjugate of minus omega. Okay. Okay. Just consider that x of minus omega you're convolving with y conjugate of minus omega in the frequency axis, in the frequency domain. Okay, that's where the omega. That is the basically I will define that as z of omega tilde. So omega tilde is basically like the the variable of the convolved signal is nothing but integral x of minus omega into um, y conjugate of minus of omega tilde minus omega. Do you agree? D omega. Basically, what I'm saying is you have to the second signal is y conjugate of minus omega. So omega you need to replace by omega tilde minus omega. Is it okay? That's all I did. Like, tell me if there is a confusion in this step. So what is x? What is your convolution? Convolution is nothing but in time domain. I'm writing for just the reference. Z of t is nothing but integral x of tau y of t minus tau d tau. That is basically your convolution formula. Now here tau plays the role of minus omega and t plays the role of omega tilde. Okay, all I did is that so basically what this says is tau for x of tau have tau as it is. For y of in the argument for y replace tau by t minus tau. So what I should do, omega I replace by omega tilde minus omega. That's what I did. Is it okay? Hello? Is it okay? Okay. If you have doubts, you ask me. Let's go forward. And that is nothing but integral x of minus omega into y conjugate of omega minus omega tilde. Because I just distributed minus of omega tilde minus omega is omega minus omega tilde. Okay? Fine. So what did we find? We basically, and if you now basically, okay. So this is nothing but z of omega tilde. Fine. Now, yes, is there a question? Okay. I think there's no question. Now you see at omega tilde equal to 0. Z of 0 is equal to integral x of minus omega into y conjugate of omega d omega. Okay, fine. Now you see what is this? This integral is exactly the integral that we need to evaluate given in the question. Is it okay?
Yes, sir.
Yeah. So all what should I do? Essentially, what should I do? I basically, okay, this is what happened here. I am convolving x of minus omega and y conjugate of minus omega. If I convolve them, whatever is the convolved signal z, I evaluate that convolved signal at omega tilde equal to 0. That is the value of this integration, this asked question. Clear? Okay. Now the way I will do now, basically what it says, you need to convolve two frequency domain signals. But convolution property says that if I convolve in the frequency domain, their inverse Fourier transforms will get multiplied. Okay. So what I will do is I will multiply the inverse. I will consider the inverse Fourier transform of x of minus omega, and I will consider the inverse Fourier transform of y conjugate of minus omega also. Use the convolution property to find this answer. Okay, first let's do step by step. Let's first compute the inverse Fourier transform of x of minus omega. First step, inverse Fourier transform of x of minus omega. Okay, what is the given question? Given question is that x of omega is a Fourier transform of x of t, and y of omega is a Fourier transform of y of t. We'll use this to find the inverse Fourier transform of x of capital X of minus omega. Okay. So what is I inverse Fourier transform? Is nothing but one integral minus infinity to plus infinity 1 by 2 pi cap. This is what I need to find out. Right? X of minus omega is there. Whatever is the value, this is the inverse Fourier transform. Now what I will do a variable substitution, omega dash defined as minus omega. Therefore, d omega dash is nothing but minus d omega. Therefore, you can show that this inverse Fourier transform is nothing but this integral becomes minus infinity to plus infinity 1 by 2 pi x of omega dash into e power minus j omega dash t, which is nothing. I can write this as minus infinity to plus infinity 1 by 2 pi capital X of omega dash into e power j omega dash of minus t d omega dash. Now you see, omega dash is just some running variable of the integration. Now what is this value? Can anyone tell me what is this value? This is nothing but the inverse Fourier transform of the function x but evaluated at minus t. Therefore, this is nothing but a small x of minus t. Is it okay?
Yes, sir.
Okay, very good. Now let us do the inverse Fourier. The second signal, what did we convolve? We convolved x of minus omega and y conjugate of minus omega. And we told that after performing convolution, the convolve signal evaluated at omega tilde equal to 0. That is the value of this integral. So first we took the inverse Fourier transform of x of minus omega. We will now take the inverse Fourier transform of y conjugate of minus omega. That's the second step. Is inverse Fourier transform of capital Y conjugate of minus omega. Okay. Again, what is the requirement? Inverse Fourier transform. Again, by definition, it's 1 by 2 pi y. Okay, I'm going to do, maybe what I will do is that, okay, let me write down, then I'll tell you. Okay, this is what I need to find. Okay, I'll call this as equation 1. But what I know is, what do I know? I know that y of t is given by integral minus infinity to plus infinity 1 by 2 pi capital Y of omega into e power j omega t t dy. All I need to do is somehow I need to bring here instead of Y of omega conjugate of minus omega. Then whatever is the left hand side, I will basically, that will be the inverse Fourier transform. Okay. So what I will do is I'll call this as equation 2. Call this equation 2. First, I will do take conjugation on both sides of equation 2. So what does it become? It becomes y conjugate of t equal to minus infinity to plus infinity 1 by 2 pi. 1 by 2 pi is a real number, so conjugating it does not change, doesn't change anything. Y conjugate of omega into e power minus j omega t d omega. Okay. Now I'll do omega dash, define another variable, omega dash equal to minus omega. Then what do I get? I get y conjugate of t equal to minus infinity to plus infinity 1 by 2 pi. That if omega dash is minus omega, that means d omega dash is equal to minus d omega. This again becomes integral minus infinity to plus infinity 1 by 2 pi y conjugate of minus omega dash into e power j omega dash t d omega dash. Now, anyways, omega dash is running is running variable, dummy variable. So I'll just put omega dash is same as omega. That means this is nothing but minus infinity to plus infinity 1 by 2 pi y conjugate of minus omega into e power j omega t d omega. Now what is, so basically this is nothing but the inverse Fourier transform what we want in as in equation 1. You see equation 1 we wanted this expression, and that is exactly this expression we have here also. So now tell me what is the inverse Fourier transform then? What is this inverse Fourier transform? IFT is nothing but y conjugate of t. Is it okay? Is this okay?
Yes, sir.
Correct. Okay. Now, what did I do here? I convolved x of omega minus omega and y conjugate of minus omega. Fine. Therefore, what I'm going the property. Okay, see here very carefully. By property, convolution property, x of t into y of t will have Fourier transform x of omega convolution y of omega. Therefore, now tell me what is the inverse Fourier transform if your inverse Fourier transform if you had x what is the first signal? First signal is x of minus omega with y conjugate of minus omega. Now tell me the left hand side. Yes. Can you tell me the left hand side?
X of minus t and y of minus t.
Not y of minus t. Y conjugate of t, right?
Y conjugate of t.
Exactly. So x of minus t into y conjugate of t. So x of minus t product with y conjugate of t will have the Fourier transform x of minus omega convolved with y of minus omega. Okay. Now tell me what to do. Maybe there's just one or two more steps remaining to finish the solution. What did we say? We need to evaluate this convolution at 0. The argument equal to 0. That will be the required answer. Now what is, so if I want to get that, now tell me what should I do? In fact, it is not just this. There'll be 2 pi also, right? Yeah, I'm saying 2 pi will be there. That is the convolution property. 2 pi will be multiplied. Yes. Tell me. Nothing. Just apply the definition. What is the definition? Definition is not simple, right? That is what this means. What does it mean? Implies 2 pi into integral minus infinity to plus infinity x of minus t into y conjugate of t into e power minus j omega tilde of t dt is nothing but this convolution at omega tilde, right? That is nothing but what? See here, minus infinity to plus infinity, x of minus omega into y conjugate of omega minus omega tilde d omega. Is it clear? This is nothing but my convolution z of omega tilde. I mean, I know it's a bit difficult to grasp. See, why did the integration come in the left hand side? Because what I know is that the Fourier transform of this signal is equal to this signal. That means I need to apply the definition of Fourier transform this, and that is basically this. I'm evaluating the Fourier transform at another variable omega tilde. Okay, that means that is why you have this expression. Means now what does mean? What does it mean? Let's say this convolution is equal to z of omega. Okay, and this is evaluated at omega tilde. Therefore, I need to find z of omega tilde. So I'm writing z of omega tilde as a convolution between x of minus omega and y conjugate of minus omega for omega tilde. Now is it clear? Now is it clear? If not, you can tell me. I'll repeat it again. Okay, maybe I will write it one step. You see, is equal to um, okay, maybe let I will what I will do is I will call x of minus omega convolved y conjugate of minus omega as z of omega. Okay, the convolved signal in the frequency domain is z of omega. Therefore, what it means is I'll write it for you like this. Therefore, what this sentence says that my z of omega tilde, where tilde is some variable, is nothing but the Fourier transform of x of minus t and y conjugate of t evaluated at omega equal to omega tilde. And that basically I'm applying the definition of Fourier transform. That is 2 pi, okay, integral minus infinity to plus infinity, 2 pi into x of minus t into y conjugate of t into e power minus j omega tilde t dt. Is this clear? Is it clear? This step? All I did is I evaluated. What I told is that this signal 2 pi x of minus t into y conjugate of t will have the Fourier transform z of omega. Now I'm just computing this function at omega equal to omega tilde. Okay, that means what? Z of omega tilde is equal to the Fourier transform with omega replaced by omega tilde. Is this step clear?
Yes, sir. Clear.
Okay, very good. Now Z of omega tilde, I know that it's a convolution of omega and y conjugate of minus omega, and then evaluate that resultant signal at omega tilde. Okay, but now you go back to the definition. How did we define our convolution? Like this. This is a convolution between x of minus omega and y conjugate of minus omega. We are going to exactly use this integral now. X of minus omega into y conjugate of omega minus omega tilde d omega. That's how we started our solution with. So that means, okay, maybe I will do, this is called equation 1. I'll call our equation A. Then using equation A, the left hand side becomes what? Integral minus infinity to plus infinity x of minus omega into y conjugate of omega minus omega tilde is equal to this guy, this same minus infinity to plus infinity 2 pi into x of minus t into y conjugate of t into e power minus omega j omega tilde dt. Now what we should do? Put omega tilde equal to 0 because that's what we wanted, right? You go back and see. We add omega tilde equal to 0, the convolution becomes this guy, and this is exactly what we want in the question also. So omega tilde at 0. Then what does it become? It becomes minus infinity to plus infinity, capital X of minus omega into y conjugate of plus omega d omega is equal to minus infinity to plus infinity 2 pi small x of minus t into y conjugate of t. Here omega 0 means e power 0 is 1. Therefore, just dt. Therefore, that's all. This is a required answer. So the required answer is that integral minus infinity to plus infinity x of minus omega into y conjugate of omega d omega can be expressed in terms of x of t and y of t as integral minus infinity to plus infinity 2 pi into x of minus t into y conjugate of t dt. This is the final answer. Is this clear? Is the solution clear?
Yes, sir.
Yeah, okay. If somewhere it's not clear, you can tell me. I can again repeat the solution. I can go over the steps again. If you have doubts, let me know.
Sir, is that a different way to redefine convolution?
Which way? So this is what we had, right? This is our general convolution formula, which we did in time domain. But this
Yes,
holds for any domain. Similarly, you can define convolution in the frequency domain also as z of omega as integral some x of omega dash into y of omega minus omega dash d omega dash. You can define it like this also. Okay. Now all I'm saying is what basically says is when you basically what did you do, you had y of this is nothing but okay, let me write it. This is nothing but maybe okay, small capital X capital Y. There's nothing but capital X of omega convolution capital
yes,
Y of omega,
that's
right?
okay. Yes, sir.
All I'm doing is that I in the integral this first omega became omega dash, but second omega become omega minus omega dash. Okay, that's what I'm doing here also. So my x of minus omega written as minus omega, but minus omega will become the omega replaced by omega tilde minus omega. See how your omega became omega minus omega dash. Similarly, omega become omega tilde minus omega. Did you get this point?
Yes, sir.
And minus basically will be same. See, you should be very careful. See, omega tilde is where you are evaluating the convolution at. So that only will come first. And then the running variable come. This minus is coming because that is how the signal, I'm taking the minus time reversed or the frequency reversed version of the signal. That's why minus is coming outside. Or maybe if you have more doubts, okay, maybe this will it make it more clear. I'm defining the convolution between x of minus omega tilde and y conjugate of minus omega tilde. Okay, no, that will only make things worse, I guess.
No, sir.
Yeah, I think this is correct. Yeah, this is correct.
Yes, sir.
Like how omega became omega minus omega dash, it is omega dash minus omega,
Yes,
but
sir.
the minus will still be intact. Is okay?
Yes, sir.
You can rework the solution with your own the variable and everything, and then these notes will anyways be provided to you. You can rework the solution and on your own in your free time. Okay, fine. Now question number 5 for today. Great that we're going at a good speed today. So find the Fourier transform of x of t equal to t into e power minus at u of t, where a is a number which is greater than 0. It's a positive, real positive number. Okay? It's a simple problem with just application of Fourier transform, properties of Fourier transform. So what we know is that if x of t is equal to e power minus at u of t, then x of omega is equal to 1 by j omega plus a. You remember Laplace transform, okay, u of t is u of t. You remember we had e power minus at u of t, the Laplace transform of 1 by s plus a. And I think last class we saw that put s is equal to j omega, you will get x for a transform. So that's why that is one way to see why this is true. Is this clear? X of omega is equal to 1 by j omega plus a.
Yes,
Now
sir.
I'm asked to find the Fourier transform of t into x of t. This is my x of t. Let x of t is this. Then I'm okay. Maybe y is sorry. Maybe I will do y of t is equal to e power minus 8 into u of t. Then y of omega is equal to 1 by j omega plus a. Then basically x of t is nothing but t into y of t. Given question is t into e power minus 8 u of t. That is called, I'm saying y of t. So I need to find the Fourier transform of t into y of t. Okay. Now it's basically an application. Go back to the table that we saw in the saw today. So t into y of t. See this kind of expression. The answer is nothing but the differentiate j times d by d omega of x of omega. Here instead of x of t you have t into y of t, right? Therefore x of omega is equal to j into d by d omega of y of omega. Okay? If it's called differentiation property in frequency, differentiation in frequency domain property. Okay, so that's all. D by d omega into 1 by j omega plus a. So that's nothing but j into j omega plus minus. Okay, maybe this is into chain rule into j. There's nothing but minus j square by j omega plus a the whole square. But j square is minus 1, minus j square is just plus 1. So there's nothing but 1 by j omega plus a square. That's all. So that's all. This is the answer. X. This is x of omega. So if x of t is equal to t into e power minus at u of t, then x of omega is equal to 1 by j omega plus a the whole square. Okay, is this fine? Fine.
Yes, sir.
So good. So we have solved 5 questions now, and it's almost 7 o'clock. What we'll do is we'll take a break for about 10 minutes, 7:10. We'll again meet back. Maybe it's. I think we'll also finish the session today a little early. Okay, I think I have one. Uh, I have exactly 5 more questions. So 5, we have completed half the number of questions. Maybe we'll meet. We'll meet back at 7:10. You can stay in the call. Then we'll continue the remaining questions, and we can finish the class also a little early today. Okay, let us resume. The next question. Question 6. So it says that if x of t equal to t power n minus 1 by n minus 1 factorial into e power minus at u of t, then show that x of omega equal to 1 by a plus j omega power n. In fact, an extension of question 5. You see, question 5, or just see, if you put n equal to 1, put n equal to 1, sorry, n equal to 2. If you put n equal to 2, 2 minus 1 is t, and 1 factor is just 1. So it's t into e power minus at u of t will have the Fourier transform 1 by a plus j omega square. Right, that's what this question says, and that's what we did in the previous question. T into e power minus a of t had the Fourier transform 1 by j omega plus a the whole square. So question 6 generalizes question 5 for some arbitrary n. Okay, for n equal to 2, it is question 5 actually. So the answer, I think, is now, at least you must know the procedure is clear. How did we solve question 5? We use a differentiation property in the frequency 6 also. So answer. So what we know is that e power minus at u of t has a Fourier transform 1 by 1 plus j omega. Sorry, a by 1 by a plus j omega. This is basically the Fourier transform of e power minus at u of t. Now what we will do? Differentiation property. Therefore, t into e power minus at u of t will have the Fourier transform j into d by d omega of 1 by a plus j omega. Differentiation property. Okay, that is nothing but t into e power minus at u of t has a Fourier transform my j into uh, mm, minus 1 by a plus j the whole square into j, and this only we saw that it is equal to 1 by a plus j the whole square. So t into a of t e power minus at u of t will have the Fourier transform 1 by a plus j omega the whole square. Now again apply differentiation property. T square into e power minus at u of t will have the Fourier transform j into d by d omega of 1 by a plus j omega the whole square. This is again, let's do it. That is j into minus 2 by a plus j the whole cube into j. So that's nothing but you have minus 2j square, which is equal to plus 2. Okay, is equal to 2 by a plus j omega cube. Or in other words, this is a Fourier transform of t square into e power minus at u of t. Or by linearity property, half into t square into e power minus at u of t will have the Fourier transform 1 by a plus j omega whole cube. Now again apply differentiation property. What it says? You multiply left hand side by t, then right hand side becomes j into d by d omega of that quantity. So then what it says is differentiation property says half into t cube into e power minus at u of t will have the Fourier transform j into d by d omega of 1 by a plus j omega the whole cube, which is nothing but j into minus 3 by j a plus j omega the whole power 4 into j. So minus 3j square becomes plus 3. and that, okay, I will go one step by step. That is nothing but 3 by a plus j omega power 4. That has a Fourier transform 1 by 2 into t cube into e power minus 80 u of t, or by linearity property 1 by 3 into 2 t cube will have the Fourier into e power minus 80 u of t will have the Fourier transform 1 by a plus j omega power 4. Is this clear?
Yes, sir.
Yeah. Now we'll do one more time. Differentiation property. Again. Then what will you get? T power 4 into e power minus 80 u of t into 1 by 3 into 2 will have the Fourier transform 4 by a plus j omega power 5. Bring this 4 down again. Then what will happen? 1 by 4 into 3 into 2 into e t power 4 into e power minus 80 u of t will have the Fourier transform 1 by a plus j omega power 5. You see here, if it is 5 here, then it is 4, and here it is 4 into 3 into 2. Therefore, it is always one less than whatever exponent comes in the Fourier transform. Therefore, you keep on doing this n times. Repeat for n times. So what will you get? Or it's n minus 1, not n times, n minus 1 times from the start. Then what will you get is 1 by n minus 1 into n minus 2 and so on till 4 into 3 into 2 into 1 into t power n minus 1 e power minus 80 u of t will have the Fourier transform 1 by a plus j omega power n. But what is this? This is exactly equal to n minus 1 factorial. Okay, that is the question. So what is the question? Show that the Fourier transform of x of t is equal to 1 by a plus j power n, and that's what we have shown. So it just repeated application of frequency differentiation property in the frequency domain. Is it clear?
Yes, sir.
Okay, great. Now question number 7. Find the Fourier transforms of the following signals. A, x of t equal to 1. B. Okay, let's do one by one. X of t equal to 1, let's do first. Now, yes, do you want to try it? How to solve? Okay, hint is as follows. If y of t has the Fourier transform capital Y of omega, then capital Y of t will have the Fourier transform 2 pi into small y of minus omega. The duality property. This is the hint.
Del divided by 2 pi.
It is del divided by 2 pi or del into 2 pi?
And del into 2
Because,
pi.
yeah, correct. Because basically, what we know is that if this were delta of t, we know that capital Y of omega is equal to 1. That is something known to you. But what Fourier transform? That's what I'm asking here. So your Y of t is equal to 1, then small y of omega. So Y of t is let's say then put Y of t is equal to delta of t. Therefore, Y of omega is nothing but 1. So by duality property, delta of t will have the Fourier transform 1, or 1 will have the Fourier transform 2 pi into delta of minus omega. But delta is a even function, right? Because it only has one impulse at 0, omega equal to 0. So that is same as 2 pi into del of omega. Therefore, Fourier transform of 1 is nothing but 2 pi into delta of omega. Is it okay? It is. If I have the time domain, I'm just plotting, okay? X of t is equal to 1 for all t. We'll have the Fourier transform. If you plot the omega Fourier transform, if you plot it, it will only have x of omega will be a impulse function only at omega equal to 0. It will have some value 2 pi. It will go to, it's an impulse at 2 pi. Everywhere else it is 0. Okay. Now, second question is Fourier transform of x of t is equal to e power j omega naught t. The answer is again simple. What I know is just from the first question, what I know, one has a into delta of omega. Therefore, e power j omega naught t into 1 will have the Fourier transform 2 pi into del of omega minus omega naught. Is it okay? Just what is this frequency shifting property of Fourier transform? Is it okay?
Yes, sir.
Okay. Similarly, C x of t is equal to e power minus j omega naught t. Fine. Not very difficult. Same logic. One has the Fourier transform 2 pi del of omega. So e power minus j omega naught t will have the Fourier transform 2 pi into del of omega plus omega naught. That's all. Okay. Now tell me, there is a purpose why I wrote C. Now tell me what if x of t is equal to cos omega naught t. How do I find out the Fourier transform? Yes. Okay. So by
Split
yes.
cos
Hmm?
e to the cos j omega t by 2 and then take duality property.
No need of duality. See this? Simple. By Euler's expansion, what we have is that cos omega naught t is nothing but e power j omega naught t plus e power minus j omega naught t by 2. Is it clear? And
Yes,
now
sir.
I have the Fourier transform of e power j omega t, e power minus j omega naught t, add both of them, divide by 2. That is the Fourier transform of cos omega naught t. That's all. Therefore, x of omega equal to 2 pi into delta of omega minus omega naught plus 2 pi into delta of omega plus omega naught by 2, which is nothing but pi into delta of omega minus omega naught plus pi into delta of omega plus omega naught. In fact, this is what we saw, I think, in today's class also somewhere in the beginning. Yeah, see, that's what we saw here. Okay, same as cos omega naught t. I've derived it using, I first derived the the Fourier transform of all one signal, that is 1, and using that I derived the Fourier transform of everything else. So I will not write it down. So you can just tell me if it is sine omega naught t, how will the expression be? E power j omega naught t minus e power minus j omega naught t by 2j. Therefore, it will be, you will have a minus here and you will have by j here also. That will be the only difference. Okay. We have finished. This is question number what, 7? Huh? 7. Good. Now let's do question number 8. Sorry. Okay. Very interesting. It's a general question which is many times asked in GATE exams in a different form. I'm giving the general question for that. Find the Fourier transform of a periodic signal x of t with period t naught. See, what did we say? We started out the definition by saying that Fourier transforms are applicable are also applicable for continuous time aperiodic signals. But that never told that it is not applicable for periodic signals. Even for periodic signals, it is applicable. Basically, it's a Fourier series applicable for a continuous time periodic signal, but Fourier transform is applicable even for a continuous time aperiodic signal. It is also applicable for periodic signal. So it turns out that for a periodic signal, the Fourier transform has a specific formula. You can generalize it to, so we know the Fourier transform formula, x of omega is equal to integral x of t e power minus j omega t dt. But for if the function is more periodic, on top of it, it's a periodic that has even more special structure. The formula can be even more simplified. And that is what this question is about. And in GATE exams, people generally ask, sometimes I've seen them asking, find the Fourier transform of a square wave, which is a continuously, it's a periodic square wave. Instead of going back to the formula, you can basically use the expression for whatever we are going to derive now. Why I'm saying is, if I use the formula, then that integration is over all time, right? T equals to minus infinity to plus infinity, and x of t will keep on having, continuously it will keep on changing. So it's it may be difficult to integrate your Fourier transform definition. But with the alternative formula that we're going to prove now, it may be easy. You will see that the answer for this is going to be based on Fourier series of a periodic signal. Okay, so answer. Okay, recall that any continuous time periodic signal has a Fourier series. What is the Fourier series? You can write x of t is nothing but sum over k equal to minus infinity to plus infinity ck e power j k omega naught t, where omega naught is equal to 2 pi by t naught. This is the definition of Fourier series. Okay, yeah. Now tell me, can anyone tell me what should I do? Take Fourier transforms on both sides. Then what happens is that x of t Fourier transform is x capital X of omega, and apply linearity property. So sum Fourier transform of sum is nothing but sum of Fourier transform. So k equal to minus infinity to plus infinity. Ck is some constant into Fourier transform of e power jk omega naught t. Now tell me, in the previous question we derived for e power j omega naught t, the Fourier transform is 2 pi into del of omega minus omega naught. But now instead of omega naught t, I have k omega naught t. Therefore, it will become del of omega minus k omega naught. Do you agree? Do you agree?
Yes, sir.
That's all. Therefore, and therefore, this is a Fourier transform. This is a simplified formula for Fourier transform of any periodic signal, continuous time periodic signal. 2 pi into summation k equal to minus infinity to plus infinity ck into del of omega minus k omega naught, where ck is basically Fourier coefficient, same 1 by t naught integral over one time period x of t into e power minus j 2 pi k by t naught, right? Because it's yeah, kt dt. That's all. This is basically the simplified expression. For all you need to do is simple. If someone asks you the Fourier transform of a periodic signal, do only one thing: compute ck. Plug this here. This is the Fourier transform of a periodic signal. That's all. You don't need to do anything else. Ck is easy to do because it's only the integration is over only one time period. On the other hand, if you look at the definition of Fourier transform, the integration is over all time t from minus infinity to plus infinity. That's how this formula simplifies your solution. In fact,
So
yeah,
we can say that a Fourier transform of a periodic signal is nothing but a series of impulse.
very good. You are correct. Fourier transform is basically a period of impulse. You're right. It's correct. Only thing is the scalar will be different. CK will be different. For depending on what the signal is, the different impulse will have different amplitude. Okay. In fact, you asked a very good question. A very good question you asked. For example, if x of t, was a impulse function, let's say a periodic impulse function. Very good. Let's say example, given that you've asked, let's say example, x of t, let's say, is a periodic signal k equals minus infinity to plus infinity, del of t minus k t naught. So how does the signal look like? At k equal to 0, you have a delta function. At t is equal to 0. At t equal to t naught, you have a delta. At t equal to minus t naught, minus 2 t naught, and so on. This is what x of t. Am I right? Fine. Now, you recall, I think in our previous session, last session or last to last session, I don't remember exactly. For x of t as an impulse, it's called an impulse train, right? It's called an impulse train. We derived that your CK value was equal to 1 by t naught for all t naught, for all k. This is what we derived. Okay. So basically, if you put this value above in this equation, so if someone asks you the Fourier transform of a impulse train, then it turns out that your Fourier transform is nothing but x of omega is basically 2 pi by t naught into summation over delta of omega minus k omega naught, k equals to minus infinity to plus infinity. Now, if you plot this, it says at omega equal to omega naught, omega equal to omega first is omega equal to 0. You should start with omega equal to 0, omega equal to omega naught, omega equal to 2 omega naught. Similarly, omega equals minus omega naught, omega equals minus 2 omega naught. Everywhere you will have 2 pi by t naught as the scaled version. Here you had 1, right? Everywhere you had 1 in the x of t. But for this, for a Fourier transform, you will have 2 pi by t naught. And this will go on both the sides. Okay, so you're indeed right that the Fourier transform of any periodic signal is basically an impulse train with different amplitude. But if the Fourier transform, the continuous periodic signal itself is an impulse train, then the frequency of Fourier transform is also an impulse train, only with the fact that it's a scaled version. Basically scaled by 2 pi by t naught. The amplitude is scaled by 2 pi by t naught. That's the only difference. Is it okay?
Yes, sir.
Yeah. Very good. You're now in question number 9. It's a very useful the question number 9 is actually a very useful concept when you study communication systems. If in your wherever, if you're working communications, or if you happen to take a course, you will encounter this particular result. So what this says is show that x of t into cos omega naught t. Okay, that is, I have some function, some signal already x of t. I multiply that with cos omega naught t. That has the Fourier transform half minus omega naught plus half of x of omega plus omega naught. Yes, can anyone tell me what is the approach I need to use? It's a very straightforward solution actually.
Apply Euler formula and then cos into e to the power j, and
Correct.
then
You are right. That's the starting point. Apply Euler's formula, then you're done. Okay, let's do that. Okay, answer by Euler's formula. What do we know? We know that cos omega naught t can be written as e power j omega naught t plus e power minus j omega naught t by 2. Therefore, x of t into cos omega naught t is equal to x of t into e power j omega naught t by 2 plus x of t into e power minus j omega naught t by 2. Now you know the answer. Just the application of Fourier transform. You go back to the table again. There's the table. Yes, see here. If I have x of t Fourier transform is x of j omega, then e power j omega naught t into x of t has the Fourier transform x of j omega minus omega naught. That's what we're going to use here. Okay. Therefore, the Fourier transform will be the first term. What is the Fourier transform? X of omega minus omega naught by 2. Here it is x of omega plus omega naught by 2. That's exactly what we have to prove. Is it okay?
Yes, sir.
That's all. It's just two-step, but it has this is a very, very important result people do in communication systems. Okay. So just for your okay, as a homework, you prove the other also. Homework is that show that x of t into sine omega naught of t, right? It was cos first. Now basically I'm saying for sine, we'll have the Fourier transform minus j into half of x half, okay, maybe x of omega minus omega naught by 2 minus x of omega plus omega naught by 2. The approach is same. Apply Euler's formula for sine omega naught t and then apply the frequency. Fine. Now, what I want to say is that these two results, which two results? This and B. A and B are also, they also have a special term, also called modulation theorem. Modulation theorem of Fourier transforms. Why it's called modulation, right? Basically, it has a very extensive applications in communication systems. So basically, when I want to communicate, what do I mean? It's a very simple example. Let's say you have a mobile phone with you and you connect to a tower and you want to communicate. Let's say you make a call to your friend. Basically, what happens is that you send a message from the mobile phone, it goes to the tower. So there is first the communication between your mobile phone and the tower with which through which is helping you to communicate, right? So basically, this is called a communication. Now, it turns out that for communicating any signal, the message will not be directly transmitted over the channel, the air. It's a free space, and the signal is getting transmitted from your mobile phone towards the tower. It's a free space propagation, right? And it turns out that the mobile phone will not just like that transmit whatever messages you're saying. It will do something called modulation. It basically what happens is it will up convert. There is a stage where it up converts the frequency. You will let's say our speech signal, let's say, is between, you know uh, let's say it occupies some frequency, right? And then there's a device called transducer in mobile phone that will convert the sound signal to an electrical signal, and that electrical signal in turn will occupy some bandwidth. Okay, now that bandwidth, it will have some frequency components. When you transmit that signal over the air, that will not be transmitted as it is. It will be modulated by a something called a carrier wave, carrier signal. Yeah, that is a very, very high frequency signal. Example, it is of the order of megahertz and gigahertz. Let's say 700, so 700 megahertz, 800 megahertz. It's a very, very high frequency compared to the frequency of the actual message signal. So basically what happens is you modulate, you multiply your message signal. So for example here, right, is x of t is, let's say, is a message signal, what you want to transmit to the air. And omega naught is a very high, very high number. Let's say it is of the order 7 into 10 power 6 hertz. That is 7 or 700 into 10 very high number, very high frequency. So you multiply your message signal by a very high frequency signal, and this is what will go through the free space. At the tower, again it will demodulate. That is, it will remove the component of cos omega naught and will recover back message signal. There are, you can ask, why is this, why should this up conversion and down conversion happen? There are various reasons for it that you will learn in if you take communication course, or if you are a communication engineer, you will know about it. But all I wanted to tell at this point is that this result has very important application in communication systems. And since this is what is called as modulation in communication, some people also call this independent property of the Fourier transform as a modulation theorem, or the modulation property of Fourier transforms. Okay, fine. So it's a very, maybe a side point which maybe or may not be useful to you. Anyways, so that's basically the 9th question. We now will solve the last question for today, the 10th question. Are there any doubts that you have till now?
No, sir.
Okay, thanks. Last question. Question 10. Find the Fourier transform of a x of t equal to 1 by t. Okay, let's do it. And b x of t equal to 1 upon 1 plus t square. Solution. So first, what I will do is recall that signum of t at the Fourier transform 2 by j omega, or 1 by 2, or j by 2 into signum of t will have the Fourier transform 1 by omega. Now, do you get any clue how to find the Fourier transform of 1 by t? Any idea? Simple duality property. That's all. Call this as y of t. Then this is y of omega. Therefore, we are asking y of capital Y of omega. Then capital Y of t is nothing but what? 1 by t. And that's what we want. The capital Y of t is exactly equal to x of t. Small x of t. We'll have the Fourier transform 2 pi into small y of minus omega. Right? That is nothing but duality property. Is it okay? But what is small y of omega? 2 pi into j by 2 into signum of minus t, minus omega. Is it okay? Because y of t is nothing but j by 2 into signum of t. And y of, I'm evaluating y of minus omega. So it becomes 2 pi into j by 2 into signum of minus omega. Okay? 2 to cancel. So it becomes signum of minus omega is same as minus signum of omega. So it's nothing but minus j pi into signum of omega. Therefore, 1 by t has the Fourier transform minus j pi into signum of omega. See how nice, just by applying the property of the Fourier transform, you can derive the Fourier transform of one signal from another signal. Otherwise, you have to, in fact, if you do the integration, right? Let's say if you were to do integration, then what you would have done? You would have done x of omega equal to integral 1 by t into e power minus j omega t into dt. See, maybe it is solvable. I'm not saying it is difficult. It is very difficult. Maybe you can solve something you can do, but still you have avoided all of them. You have nicely just exploited the properties of Fourier transform All you had to do is only two things. You need to think which other Fourier transform in the frequency domain has the form 1 by omega. Now 2 by j omega, it's some c times 1 by omega, where c is 1 2 by j, right? So you can manipulate that 2 by j omega to just get 1 by omega, like how I multiplied signum of t by j by 2 into signum of t, right? And then apply duality property. So when you practice many problems, you will automatically start to connect things like this. Okay. And the second b part is x of t is equal to 1 by 1 plus t square. Okay. Any thought about how to, same I'm telling you right now, do again duality property. But for duality property, I need to identify some Fourier transform pair like this. Now, which Fourier transform pair should I identify for this? You have solved this in class, this week's lectures.
E minus 80.
Ah, correct. You're right. Very good. What you should do, B part. What is recall? This is the first e power minus a mod t has the Fourier transform 2a by a square plus omega square. Okay. Therefore, e power minus mod t will have the Fourier transform what? 2 by 1 plus omega square, or half into e power minus mod t will have the Fourier transform 1 by 1 plus omega square. That's all done. Now, this is 1 by 1 plus omega square, but I'm asking 1 by 1 plus t square. Exactly, duality property again. What I'll do is I'll call this as y of t. I'll call this as capital Y of omega. So what I know is that small y of t has a Fourier transform capital Y of omega. So capital Y of t will have the Fourier transform 2 pi into small y of minus omega. Again, duality property. Okay. And what is that? 2 pi into 1 by 2 into e power minus mod of minus omega. But anyways, mod of minus omega is same as mod of omega. 2 to cancel. Remember, pi into e power minus mod omega. That's all. Is it clear?
Yes, sir.
Yeah. Otherwise, what you would have done, you would have again done the integration. That is another straightforward approach. Minus infinity plus infinity, 1 by 1 plus t square, e power minus j omega t dt. I don't know. This is a complicated integral, at least. At least the first step, it's a complicated integral. You need to put some efforts, or you need to do variable substitution or by part, something you need to do. It's not easy, as easy as this. But this is a very easy approach, provided you identify this as a starting point. If you remember this, then you know the answer. Very simple. So that's why it is good to remember the Fourier transforms of some standard signals. Like, some standard signals, it's good to remember. That can help you to apply some properties over them and find the transforms of some other signal. Okay, so I have only this much today. Are there any questions?
Sir, will you sum up question number 4 once again?
Yeah. Question number 4. Okay. This question,
Yes.
I will tell you what I did at a high level, and you connect all the dots in your free time. What I'm asking is, what is being asked is, evaluate this integral, which has some x of minus omega, y conjugate of omega, d omega. But I want to find this number in terms of x of t and y of t. That is the question. So first, what I did is that, so you see, why did I get the idea that I need to go with convolution? The basic reason is because in convolution only you will product two signals and then integrate over them. Right. That's why you see I'm productifying two signals and then integrating over all omegas. So that means somehow I need to bring in the convolution property. That is the first thing. Okay. Now, if I bring in convolution property in the convolution in frequency domain, then that means multiplication in time domain is basically the corresponding inverse Fourier transforms will multiply in time domain. So first, what I did, I identified which two signals should I convolve in the frequency domain so that convolved answer will be helpful to find this actual question. So what did I do? I convolved this. So basically what I did is I took this convolved x of minus omega and y conjugate of minus omega. Okay. And then I got that, I call that as z conjugate of omega. Okay, omega tilde, z conjugate of omega, z of omega tilde is defined as this integral. Okay, x of minus omega into y conjugate of minus of omega tilde minus omega, because this is because of the same reason that if I convolve y conjugate of minus omega tilde should be replaced by omega minus omega tilde. Sorry, omega tilde should be replaced by omega tilde minus omega. That's what we did here. I think the person dropped the call, whoever asked. Okay, you're back. Okay, see, yeah, I think you're back. So what I did is that I took two signals x of minus omega tilde and y conjugate of minus omega tilde. I convolved both of them. Is this convolution formula clear?
Yes, sir.
Okay. And now what I did is basically this is what I got after simplifying. Now basically what it says is if I put omega tilde equal to 0, then I get this expression. This is exactly what I need to find here. So what does it say? It only says me one thing. You convolve x of minus omega tilde and
So
y conjugate of
after that, I got it.
okay. Yeah, I'll tell you. So basically what I did is that I convolved these two and the convolved result I need to evaluate it at 0. That is what is my actual answer. So instead of now basically convolving them in the frequency domain, I take the inverse Fourier transform and then multiply them. That's what I'm doing. So what I have is that x of minus omega tilde or x of minus omega. See, after all, they're all dummy variables. Okay. So if you write the inverse Fourier transform of x of minus omega, it comes out to be. Okay. Similarly, if I compute the inverse Fourier transform of y conjugate of minus omega, it comes out to be yeah, y conjugate, small y conjugate of t. Therefore, if I convolve x of omega and y of omega, if what is given in the question is 2 pi into x of t into y of t is basically the has a Fourier transform x of omega convolved y of omega. Okay, this is a convolution property. But what I want is I want to convolve x of minus omega and y conjugate of minus omega. And that means their corresponding inverse transforms should multiply in the time domain. But I know that x of minus omega has the inverse Fourier transform x of minus t, and y conjugate of minus omega has the inverse transform y conjugate of t. Therefore, I multiply them in the time domain. I multiply by 2 pi. That is because of property. So this is my Fourier transform relation. But this is not what I want. I want to evaluate this convolved expression at 0. Basically, the argument omega equal to 0, right? Z of omega. And that's what I need to do. So what I do is that first of all, I write down the expression for this Z of omega using the definition of Fourier transform. Okay, that is 2 pi into x of minus t into y conjugate of t e power minus j omega tilde t dt is Z of omega tilde. Is it clear? Is this clear till now?
Yes, sir.
Yeah. Now all you need to do is put omega tilde equal to 0. Okay. Okay. This is basically the definition of Fourier transform. But z of omega tilde itself is the convolution of x of minus omega and y conjugate of minus omega. Therefore, again put that expression here. Now what you do? Put omega tilde is 0 on both sides. You will get this expression. And this is what you wanted actually. So this integral x of minus omega y conjugate of omega d omega can be evaluated in terms of x of t and y of t as integral 2 pi into x of minus t into y conjugate of t dt. Is it okay?
Yes, sir.
Yeah. Okay, are there any other questions?
No, sir. Thank you.
Yeah. Okay, then next week we will meet at the regular time and regular day of Friday. Okay, not today was an exception. Next week we'll again meet on Friday, same time, same link. Okay.
And next week we will discuss about.
I need to see. I forgot. I don't remember. I think we will now move on to discrete. So until now we have dealt with continuous time Fourier series and Fourier transform. Now we have to go for discrete times Fourier analysis of discrete time signals. I think so. Let me check and I can get back.
Autocorrelation.
Autocorrelation. I don't know if that is a part of this course.
In
Uh,
PDF, there is something about autocorrelation. Week
where?
7. Week 7.
Week 7. Okay. Okay. But autocorrelation is not something very different. It's basically convolution. So, okay, let me tell you. If you know convolution, then it's nothing, no rocket science. What you do is, so x of t convolve with y of t is basically convolution of. So maybe I'll write like this. X of t convolve with x of t is nothing but convolution of x of t with x of t. Is it correct? But if you write a convolution of x of t with a time reversed version x of minus t, if you convolve x of t with x of minus t, that is called correlation, autocorrelation of x of t. It's just this much. Or similarly, if you do x of t convolution y of minus t, instead of y of t, if you do minus t, then this is called cross correlation. Cross because it is two different, x and y are two different signals. So it's called cross correlation of x of t with y of t. Here then in the above it's called autocorrelation because it is the same x signal, same signal x, but with time reversed. Okay, that's all. So it's basically convolution operation at the root. At the core, it is a convolution operation. It's just that you convolve slightly a time reverse version of the same signal. Okay, so for example, so x of t convolve x of minus t, or is that what? Okay, y of minus t. What does it become? X of tau into y of minus of t minus tau, right? D tau is nothing but integral x of tau y of tau minus t d tau, and this is exactly the expression for correlation you would have seen. Is it clear?
Yes, sir.
Yeah. Basically, what it says is why is the meaning correlation, right? Correlation tells how much two signals are very similar. That is the meaning of correlation. How correlated they are means if I tell about one signal, how is it correlated to another signal? How two different signals are similar? Now, what this does is it takes x of tau and it delays by the same the other signal also you take. Let's say if you instead of y you had x, right? Then what it would have done? You take the same signal at tau and tau minus t at two different time instances and you multiply and integrate over all such tau. What it says is it will basically tell you how two signals are correlated. If let's say the correlation is 1, that means that the two signals across time are basically going to be equal or they're completely correlated. If I tell you the signal value at let's say t equal to t1, I will be able to very truly accurately predict the value of the signal at some other time t equal to t2 if the autocorrelation turns out to be delta function. Is it okay?
Yes.
But I think these are little more slightly advanced topics because you need to understand correlation. You need to interpreting them physically is not something very easy. It's slightly advanced topic. But I think for the purpose of this course, it is enough to know that the correlation can be expressed as one function is actual function, the other function is a time reversed function of the second function. That's all. Okay, any other question?
No, sir.
Okay. Okay, then we will meet again next week, Friday. Okay, then thank you all.
Thank you, sir.